Hello. All right. Okay, welcome back, folks. Welcome back. Okay, so today I want to continue with the topic that we started last time on smooth curves and extend it to surfaces today. Excuse me. And then start talking about meshes and geometry processing. So last time we ended up starting with Bezier curves. And as a reminder, we got here first starting to talk about smooth curves, right? And I started with Hermite splines, which are a way to use a polynomial function in order to smoothly interpolate right between 2 points when we were given the points and also the tangents or the derivatives at those points. And then I moved on to Bezier curves, and I said, okay, so they're used in various places, and I said it sort of has a bit of a weird definition, but this ties in very naturally to the conversation that we led into. How's that volume? Is that a bit better? Echoing a bit less? Okay. And I said, okay, this is sort of weird definition, so I'm just going to connect it for you back to Hermite splines since we started there, and I just said if you have these 4 control points which define the Bezier curve that we want here, which is going to, again, be given by a cubic polynomial, then the definition here is going to turn out to be that the tangent vector at P0, the curve will go through P0, and the tangent vector there is going to be given by 3 times P1 minus P0, and the exit tangent vector is going to be given by 3 times P3 minus P2, and the curve will go from P0 to P0 to P3, and have a shape that has that kind of tangent at beginning and end, okay? And I said then good exercise to derive this matrix form that we've done for the other 2 splines that we looked at, and I gave you a little demo. Okay, so that's where we ended up of cubic Bezier curves. Okay, so this time I want to move on with this and show you like a totally different way that Bezier curves, the exact same blue curve that we looked at before, a totally different way that you can calculate that curve or draw that curve, sort of a procedural algorithmic method to this, okay? And then we'll see sort of how they join back up. But there's a lot of different ways, mathematically and geometrically, to look at these Bezier curves, and these are themes that come up a lot in trying to craft these smooth curves. So let's look at evaluating Bezier curves using the de Casteljan algorithm, which is a recursive algorithm. And we'll start with quadratic Bezier curves, which means that instead of having 3 control points, we just have 2 control points. I might be like, oh, what is the tangent vector here? How does that define? We'll get to that in a second. But let me just start with 3 control points, and we'll see the algorithm, and then extend it back to the 4 control point case. So here we just have 3 control points, B0, B1, B2, say 3D positions in space. And so here's the procedure, okay? So first, we start by drawing a few additional points. This is for a parameter, based on a parameter t. And again, you can think of this as that parameterization, the parameter, rather, for eventually like a p of t, where t varies from 0 to 1, and that'll give us the curve tracing from the first control point to the last control point. So we take that t parameter, and then we insert conceptually, we insert another point here that's labeled B10 that you can see there. Okay, so this point right here. And it's just t distance between B0 and B1. Okay? And we do the same for this segment over here. Ending with another point, we'll just call it B11. So here the upper number sort of refers to one level of subdivision here. And the lower coordinate is just, label so B10 and then B11, okay? And then we're just going to do it again for those 2 new points. So we'll join them by a segment and then subdivide that segment again in the same ratio given by this t parameter. And that'll get us to a point B20, okay? Now we have just 1 point. We sort of went from 3 control points down to 2 intermediate points down to 1 point. And at this stage, we can't continue this procedure, and that is going to be a point on the curve, on the final curve that we're trying to draw, that blue curve from before, okay? And so here's that curve again. So this is an algorithm that for different t values will give you this sort of, very simple, conceptually simple procedure in order to get a point on the curve, okay? Sort of like a corner cutting algorithm, if you can picture that, right? You start with almost like a triangle, or at least two edges of a triangle. You sort of chop it off, and then you have a point, and then you sort of subdivide again, and that gives you 1 point on this eventual Bezier curve. Now you could imagine this being quite general. So if I gave you, instead of a starting triangle or 3 control points, let's say I gave you 10 control points. You could imagine exactly the same algorithm would work, right? You just cut off each of those corners on that line segment. You end up with 9 points then. You do it again, you end up with 8 points. Then you end up with 7, 6, all the way down to 1 point. And that point would be a point on the Bezier curve for order 10 for that much higher order case. Okay? Successive linear interpolation is also part of one of the themes here. Okay, so now we can think about it for the cubic case that I showed you before, and I described those derivatives as being 3 times that distance from the adjacent control points. Anyway, let me just show you a little animation that I think just does a great job and better than I could do by waving my hand. So here we go. So let's go back to the quadratic case. So here are those 2 control points moving as a function of t. Here's t0, and then up to t1. And then on that green line segment, you can see there's a green dot, and that green dot is moving in the same proportion, that same t ratio. Here's the cubic case, okay? So we have the 3 purple points subdividing into, again, to 2 green points, and then now a final point, blue one. It's on the subdivision between the 2 green points, and that blue point traces out, as you vary from t equals 0 up to t equals 1, traces out the final Bezier curve. Okay? If you move those control points, okay, you get a sense of how the shape of the blue curve will change. This animation is sort of give you a very visual intuition, I think, for how that's shaped out. And you can put these points in, for example, 3D instead of on a plane. So if you sort of visualize it here, you can see those 2 black control points sitting out in space. They don't need to be coplanar with the other 2. So they could be at different positions. And you can see how you can twist this curve, right, in 3D space if you did that. Okay, great. And you could go into higher dimensions too in a couple ways. So you could have more than 4 control points, obviously. Each of these control points, they could be on 2D points on a plane. They could be 3D points in 3D spaces that I talked about here. And in general, they could be vectors in Rn or quite general, linearly interpolable objects. So, but for our purposes in class, 3D space is going to be a good place for us to concentrate. So back to this 4-point case, let's just take a closer look at the linear interpolations here and see what else we can figure out from this. So here's a point B10, B11, B21. Here again are these connecting points that we can draw between those new intermediate control points. Now we subdivide again, join those, and then the final point over here. So B30 in this case, for this cubic Bezier curve, is going to be a point on that final cubic Bezier curve. And here are all the t ratios again. Okay. Okay. So if we, okay, good. Okay, fine. Okay, great. So if this function, if we call it x of t from 0 to 1, then that's going to be the position at parameter value t in general. And we can use that to sort of think about when we did that subdivision scheme, how to evaluate where that point is algebraically. We can derive the algebraic form from that geometry just by considering that tree of control points. So if you look at this pyramid on the left-hand side, we start with B0, B1, B2, B3. Those are the input control points, 4 control points, right, for this cubic Bezier curve. And then when we go to the moving up the pyramid one level, B10, B11, B12. How do we get those? We're just interpolating the two control points in the level below, specifically to get B10 over here. We're multiplying B0 by t, and we're multiplying B1 by 1 minus t to interpolate to get this point over here. And in fact, every left and right triangle that meet at a vertex on this pyramid is done exactly the same way, right? This is implies a multiplying by t, and this implies a multiplying by 1 minus t. Once you get to this level and you want to go to B20, it's again multiply by t here, multiply by 1 minus t, add them together and get that control point. All right? Okay, great. So let's just pop back one level so the math is like not quite so filling the slide, and just go back to the quadratic case. So here we got 3 control points to start. And what do we get? So at this level here, we can just write it out. Right here it is, 1 minus t times b0 plus t times b1. b11 equals 1 minus t times b1 plus t times b2. b20, that point right there, from that pyramid would have been 1 minus t times b10 plus t times b11. We can just substitute it in, and you'll detect a pattern that, is very regular and will look, very orderly and symmetric and make a lot of sense, I hope. So this kind of structure shows up in lots of places in algebra that we've looked at in other sort of scenarios, but let's just do it all out. Okay, so the final point on the curve, this is the Bézier position for parameter t, is given by just by substituting all this stuff in, is 1 minus t squared times b0 plus 2t times 1 minus t b1 plus t squared b2. Okay? And you can see the pattern here. So if you multiply again each of these by t's and 1 minus t's, you'll see the pattern that sort of emerges. And in general, what's going to happen is that you get the set of algebraic equations for those coefficients. What coefficients do I mean? That coefficient right there. 1 minus t squared is the coefficient of b0. 2t times 1 minus t is the coefficient of b1. T squared is the coefficient of b2. So in general, you get what are the coefficients? Bn of t, we'll call that the position on a Bézier curve of order n at parameter t, is equal to, if you're considering these different levels, Bn of 0 of t, and it's given by, you could write it in this form. Bj's are the control points. The coefficients are given by this capital B nj of t. And I think I've labeled it here. Great. Okay. Control points, Bernstein. Okay. So the coefficients here are given by Bernstein polynomials, so-called Bernstein polynomials. These are scalar polynomials of degree n, and they're given by this kind of a thing, right? What is it? So the scalar quantity Bn of I is given by n choose I times t to the I times 1 minus t to the n minus I. Okay? Good. Let me just see. Okay, great. Great. Okay, so let's just look at it for n equals 3. Okay, so sort of check. So we did it for n equals 2. Let's look at it for n equals 3. What's it going to look like? Okay, so let's say B0, B1, B2, B3 are given by points in 3 space. Okay, so very specifically, B0 is a point at 0, 2, 3. B1's at 2, 3, 5, so on and so forth. Okay, so you got 4 control points sitting in 3D space. No problem there. And then if you plug into this Bernstein polynomial from before, then what do you get? It's 1 minus t cubed. It's 3t times 1 minus t squared. It's 3t squared times 1 minus t, and then t cubed. Okay? So that's given, and the numbers that obviously come from the n choose I term. Okay? And it can go for quartic and quintic and so on and so forth. Okay. So this is sort of put into sort of an algebraic form. You can see how the polynomial coefficient equations there come out in this very orderly fashion, okay, just from these successive linear interpolations from that corner-cutting algorithm, a recursive corner-cutting algorithm. And by the way, when I said you could try to derive that matrix form, right, for the Bézier curves, I said you could do that now that I told you that the derivative is going to be 3x. Okay, remember there's a funny 3 term. I said this seems a bit arbitrary, but just go with it. And so you could take it back to the Hermite-Spline definition and calculate out what this matrix form for Bézier curves could be. You could do it a different way now, because now if you look at this, you could recognize that there's 1 minus t cubed term, this 3t times 1 minus t squared term. Those are what? If you recall from our analysis last time, those are giving us the basis functions for all polynomial functions, and those basis functions are specific to this Bézier curve. Okay, so the Bézier basis functions turn out to be the Bernstein polynomials that we just looked at. And in the general case for order n, it's given by this coefficient equation that we had a couple of slides ago. And for the case of 3, this cubic Bézier curves with 4 control points, here they are, and they happen to have a specific shape. I don't have anything more to say about the specific shape, just that they do exist. They're linearly independent in the sense that this is a basis for all cubic polynomial functions of t. Okay, and that's kind of how it works out here. All right. So one thing I said is that you could have high-order Bézier curves. I said you could start with 10 points. So here's an example. Okay, so no problem. 10 points. I told you the algorithm. Should cut all the corners, keep cutting corners, and you end up with points and trace out this blue curve. Seems great. Okay, so I guess if we ever need to control, like some curve, we can just plonk a ton of control points down, and Bob's your uncle. Turns out this doesn't work very well. Okay, so high-degree Bernstein polynomials are kind of hard to control. It's uncommon to use this. So if you try to move one of these curves, it has like a ripple sort of effect over like a fairly large portion of the curve. It's just not very, you can do it, but it's not very common. It's much more common to spline them together. That is to connect multiple cubic Bézier segments, cubic curve segments, okay? And I showed you a demo of that last time. So this one, for example, is composed of, I guess, 3 cubic Bézier curves. There's one here, maybe 2, 1, 2, 3, 4, 5. Yeah, I'm not exactly sure. Anyway, it doesn't matter. You get the idea. It's not one Bézier curve with a ton of control points. It's 4 control points at a time defining a segment, and so on and so forth. And this is very widely used in fonts. So the stuff I've described before in the Baskerville case it's very common to use Bézier curves, cubic, or maybe in some cases quadratic versions. And you can see how you can make corners on these things by just choosing the control point so that the derivative is not continuous at that case. So speaking of continuity, let's just look geometrically at what's required to achieve this continuity. It'll be pretty geometrically intuitive, I think. Okay, so let's say you have 2 Bézier curves, a green one and an orange one, and you want them to describe a curve, a spline curve, by connecting them. By the way, you should have to think about the bookkeeping on this a little bit in terms of the parameter term. Up to this point, all the derivations have been in terms of t going from 0 to 1, okay? And if you want to put them together and you want to put a whole bunch of these together, then maybe this is the kth portion of a spline, this is the k plus 1th portion of a spline, okay? So you might need some, in parameter space, you might need to think about that addressing a little bit. I'm going to ignore that sort of bookkeeping detail here. It's a little obvious that you can't be 0, 1 for all of them, right? Okay, so anyway, let's say we had these two and we want them to have a certain amount of continuity. So if we just choose arbitrary control points, in general, the continuity at this point here is not guaranteed at all, right? If the left curve and the right curve don't share a coincident control point at that connector, then you just have 2 totally separate Bézier curves sitting in space, not touching each other at all, right? If they are the same, so they share one control point, then you have C0 continuity. Okay, so if you have A of n, the last control point for this A curve, and B0, the first control point for the next one being the same, then you have, okay, they're connected, great. But you might have a corner. Maybe that's what you want. Let's say you want it to be smooth. Let's say you want C1 continuity. Well, what do you need? Well, basically, you need the derivative here and the derivative there to, match, right? And you can convince yourself that, in a number of ways. I told you that the derivative is given by 3 times the distance of that control point. So in that sense, if you work from there, it's not going to be surprising that you want these segment lengths to be the same. If they're not the same, you might sort of think about that too. Geometrically, it might be actually continuous there. But as you're moving as a parameter, right, t is increasing at a constant rate, you'll sort of be going at a certain speed, and then you might hit that transition point, that one vertex there that connects them, and then you might be moving at a different velocity, okay? So there might be a geometric continuity versus a parameter space continuity there. You can think through those issues, but I'm not going to harp on it here. The third thing is that maybe C1 continuity is not enough. Maybe you actually want it to have a continuous second derivative, a little bit smoother, and it turns out you could show that in order to achieve that, you need this geometric construction, which is sometimes called an A-frame construction, okay? It just turns out that you're going to need, in addition to these two segments being one-to-one, you also need these segments here being one-to-one, okay? And they have to meet at a shared point here, an imaginary shared point here, okay? I'm not going to prove that. It's a fact. But you can kind of see how some of the properties of the underlying curve in terms of its continuity can be, you can derive it in terms of some pretty simple higher order properties on just the control polygon here. Yeah? Sorry, C2 continuity just means the second derivative of this curve is going to be continuous. So what does that mean? So literally you take, there's a P of t, right? I think I call it x of t here, okay? So let's say x of t is running along this curve. You take the derivative, x prime of t, so C1 continuity means that's continuous, and then x double prime of t, that second derivative is what I mean here, that's going to be continuous. So without the A-frame, you could have continuity at that control point, but you might have a break in the second derivative. Okay. A few other things. So that's sort of nice. Okay, so there's some properties of these, splines that come from the control net. There's a few other things. Let me just recap. So these Bezier curves interpolate the endpoints. So for cubic Bezier, B0, that control point is equal to, B of 0 is equal to the first control point, and B at parameter 1 equals the last control point. We talked about the tangent case. It's 3 times the difference between the two adjacent control points. There's another property here. There's an affine transformation property. So here's the thing. Let's say I give you a Bezier curve, and then you plonk it into your graphic system, and we've talked about transforms. So let's say, okay, great, I've got this curve in space. Before, I just had a triangle or like a little quadrilateral, but now I've got like this sort of smooth thing. Okay, great. But then I want to stick a transform on it, and so I pass it through some affine transform, like the 4x4 matrices we talked about, and I know what's going to happen if I had a quadrilateral, right? I'm just going to get the transform version of that quadrilateral, and it's going to still be a quadrilateral. But here's a question. So if I transform this Bezier curve, is it still going to be a Bezier curve? So I know I can transform the control points, but if you think geometrically, if I took every single point along that Bezier curve and transform each of those, that would be a curve. Does that curve correspond to the Bezier curve from the transform control points? I don't think you have to work so hard to convince yourself it's true, but it's not like, it's not on face obvious, okay? But it turns out it is, okay? So that's a really nice property. Transform the control polygon, or once we talk about surfaces, transform the control surface, control net of control points, and the underlying curve or surface will be well-defined, okay? So that's good. There's another property, which is kind of nice, the convex hull property. So the examples I showed were kind of simple. Most of them were just 4 control points, like in a certain ordering, so that the curve was obviously inside that convex hull. But you could sort of imagine certain twist cases. You're like, I don't know, is it in... this is a nice property, okay? Where is that curve in space? How is it bounded? It sits within the convex hull of those control points. That's another thing that you could show. And you can show a lot of these just from first principles geometrically by the corner cutting algorithm. Okay, so the corner cutting algorithm is actually really a useful property if you wanted to go down trying to convince yourself in a proof-like form of this. Okay. By the way, that's the reason that that's sort of a nice property. Actually, I'm going to mention this. Okay. Okay. So another thing you can show that I didn't put on here is that if you take a Bezier curve by 4 control points, and then you do that subdivision scheme that I talked about to get, the cutting the corners off until you get 1 point on the curve. Let's say you took that 1 cubic Bezier curve and then you just chopped it right there into 2 halves, okay? You can show that the left half is still a cubic Bezier curve and the right half is still a cubic Bezier curve, and the control points are just going to be given by some of those intermediate points, the most obvious version of those intermediate points for the left half and the right half. So the subdivision theme here goes pretty deep. You can take a given control point and break it in half, and break it in half, and break it in half. So if you wanted to use a recursive algorithm to know when can I draw it and be sure that I've gotten a good curve, because I've written a rasterizer, for example, that knows how to draw lines, for example. Okay, so when can I stop? This convex hull property is pretty handy, okay? Because you know that if you get 4 control points and they sit on a line, or very close to a line, you know that the curve is going to sit within there. So once the 4 control points, after you subdivide, once you get them close enough to a line, then you know that you've squashed the inner curve to lie within there, and then you can say, okay, now I know formally I'm good enough, and I can stop and just draw a line instead. And how close does it need to be? That'll depend on your resolution of your final drawing, your frame buffer you're putting it into, whatever. Okay, so that's another way this convex hull property can be useful. Okay. Let me switch gears and, by the way, so this is like scratching the surface of like smooth curves. There are so many smooth curve representations out there that are good for different things. There's B-splines, there's NURBS, there's lots and lots of stuff out there. And many of them, stem from some of the similar principles that we've seen here. Basis functions. What are the basis functions for these curves? And, applied onto the control polygons. So control polygons control points are, very, very common in how you sort of set up or define the curves that you're trying to create. Basis functions on top of those, subdivision schemes, algorithms that do corner cutting of this kind. All right, so you're going to sort of a flavor for all of those things, but there's many, many different species of that. Okay, same can be said for surfaces. Let me talk about surfaces a little bit. So the simplest extension from the stuff we looked at, from Bezier curves to Bezier surfaces, is by doing Bezier patches. For example, a couple of very famous early examples. There was Ed Catmull is, like the head of Pixar, maybe still. I sort of haven't checked recently. Okay, and back in the day, Ed Catmull worked on, amongst other things, how to represent smooth surfaces. Okay, back in the early days of graphics. So Ed Catmull's gumbo model is composed. You can see there of little almost look like little rectangles, but they're curved rectangular patches, if you will. So each of those is a Bezier a cubic Bezier patch. Okay. You can also use it to do things like form smooth shapes like a teapot. And a teapot is a very, very common model that's used in graphics still. So what is a cubic Bezier curve? It looks a little bit like this. So if I give you, instead of 4 control points to form a curve, I give you 16 control points, 4 by 4, and you can see that the control points are sort of like directing where the proximity of that surface is. It goes through the outermost 2 by 2 control points. As you can see, the corners, they interpolate those. The surface passes through those. Elsewhere, it's going to, be curved and be influenced by the control points, but not pass through them. So how do you define this? Let me go to this animation source again, and I'll talk through it as we go. So the idea, the high-level idea is we're just going to take each of the lines. So we have a 4 by 4 net, right, of points. We're going to take a 4 by 1 set of points that's on a line of the grid, and then we're going to form a cubic Bezier curve of that. That will give you, as you can see, with 4 cubic Bezier curves here. And then if we pick a common parameter t, against t, again, right, t is going to interpolate from 0 to 1 from one end of these curves to the other end of these curves. So let's say I pick t 0.4 here. Okay, so then I get, for each of those curves, a point. Those would be the points in blue on this picture. I can take those 4 points and form a cubic Bezier curve through that. Does that make sense? So you can see that's the blue curve that you see here. And then if I think of that blue curve sweeping out a surface, as t runs from 0 to 1 along the gray curves, that swept surface is the definition of this cubic Bezier surface. Okay, so let's just see that in animation. So here's 4 control points. Let's pick these 4 lines. Let's say the control points happen to be here. That would define these 4 Bezier curves. If we pick t running from 0 to 1, or run from one side to the other, those 4 blue control points define a cubic Bezier curve. That's shown blue here. And so as it sweeps out from t equals 0 to 1 along the gray curves, that swept surface is the final cubic Bezier surface. So there it is. And then if you move these control points, they will influence the shape of the surface by pulling it in certain directions. Okay? Yeah. One second. That's actually not made with cubic Bezier. It's not made with cubic Bezier patches. That's actually a subdivision surface, I believe. I looked it up. Sorry, ask your question? Yeah.
Does it matter if we, which sort of, direction we go first? Like, if we go, this?
Yeah, great question. So the question is, does it matter which direction we go first? This is sort of like a separable definition, right? You sort of pick one direction to form these 4 Bezier curves on, and then you do the other direction. So what happens if you switch that order? What if instead of going horizontally first and then vertical, you go vertical first and then horizontal? Good exercise to convince yourself that those are exactly the same. Okay? And you could try to do it in 2 ways. You could try to do it geometrically based on this corner cutting argument, or you can do it based on the algebra. And I'm going to talk about both of those. Did I see another question over here? Yeah. Say that one more time. The gray curves, you mean? Oh, okay. Yeah, so again, okay, good question. So, I'm sorry. So the question is, how do you get those gray curves and the points along those gray curves? So here, each of these is what we talked about. So you have 4 control points giving you a blue curve. Each of those is a cubic Bezier curve. Then at this point, how do you get that point along there? Is that right? So that is, if I choose t equals 0 to 1, that will define a point along each of those gray curves. So I choose the same t value for all of them. That gives me these blue points for the same t value. And for that same t value, then I go in the other direction. Call it a different parameter, s, and run s from 0 to 1, and that sweeps out that other curve. Does that answer your question? Good, thanks. Yeah. Oh. Go ahead.
Would it work out the same if you do the column direction first?
Yeah. That was the question. Another question that was asked. Yes, you can convince yourself. It's a good question. So, on face is not obvious, but it does. The answer is yes. But good to sort of try to convince yourself of why that would be the case. Yeah.
How does, an artist or user actually, create shapes out of it? Is it just dragging the control points? That seems really
Great question. So the question is, okay, this seems all great and good, but so if an artist wants to use this, what are they going to do? Sit there and try to drag these, control points into different shapes? And the answer is originally, yeah. Okay, which is really hard. And then you want them to sort of glue together. I'm going to cover that next. It's basically like a surface version of continuity that I talk about in the curves. Later in the course, we'll touch on how you can try to build up. Okay, so the answer for Bezier curves is exactly that, which is better than trying to define it in some other way. I mean, you have to define a smooth surface in some way. But control over curved surfaces is very difficult in general. We'll talk about subdivision surfaces next when we talk about meshes. That's a different way to get it, which actually sort of generalizes the subdivision, the corner cutting scheme here on surfaces. That's cool. And then actually sort of a more common way is to use all these techniques in order to form create surfaces in general that form like a character's face, and then provide control, like higher level controls. Like if I change this parameter, then you might move your face, like you might smile, okay? And those are called rigs. So you provide rigging parameters that are more semantically meaningful, but they drive some underlying representation. Does that make sense? So it's not, so it sort of needs to get built up. It's a hard problem. Another question over here before I move on? Okay. All right. So just a review. So visualizing, did I say anything different? No, I already covered this. Great. I beat this to death now. Okay, good. So evaluating Bezier surfaces for parameters UV. Okay, a UV is similar to like on the, like on a texture map or something. This UV here just refers to sort of, if you imagine starting with a quadrilateral, okay, then U and V would be sort of like the horizontal and vertical coordinates on that. And then you have these additional control points that put it into a curved surface patch. So the indexing comes from, as you can see at the bottom right there, a little square conceptually in parameter space running from UV00 up to UV11 on that square. And that will map conceptually that unit square onto the surface. By the way, that's a way you can get texture coordinates onto this thing in a very convenient fashion. Okay. So you could, one way you could evaluate this is a separable manner in 1D using this de Castro algorithm. So how does it work? Well, very mechanistically, just like I covered it, right? You take each of the 4x1 control points that form, say, the horizontal lines of this grid, and you use the de Castro cutting algorithm in order to get a position on that curve for a particular a U value. Before I use T for curves, here U just refers to that same parameter, linear parameter, but say for the horizontal direction. And then you get each of those 4 points, and you figure out the curve in the opposite direction that's going to run along a V parameter, and you do corner cutting on that set of 4 control points in order to arrive at the V position. So sequentially you do U, then you do V. And the question before about does it matter which way is like if you do V first and do U in this algorithm, do you get the same thing? And the answer is yes. But, maybe not super obvious without thinking about that a little bit. So that's one way. And that can be visualized in this form. So the control points here numbered from 1 to 16 on the outer 2 edges of this diagram. So lerp here is linear interpolation. It's this linear interpolation according to this parameter T. So the pyramid that we were looking at before, you take 4 control points, linearly interpolate them down to 3, down to 2, down to 1. That gives you a point on the curve. You do that for each of those 4 sets of control points. So those 4 pyramids in blue coming towards the center. That gives you 4 final points. Those are the blue points in that animation. And then we do a final interpolation in the other direction, and those are given by the green lerps here, forming another final pyramid to end up with finally one node, that node which will represent a point UV on the surface. So a visual form of what I just said on the previous slide. Another way, of course, would be to do it algebraically. So, and actually, I can walk through this, but I think just the fact that this is separable and then following the algebra through sequentially in first one dimension in U and then in V is what this slide shows. So I'm not going to labor over the steps in the derivation. But we have the Bernstein polynomials, and this point along the curve of degree n, the moving curve, is given by this equation. And each of the points that are defining the control points for that moving curve will come from the 4 other control points. So if you write it all out, this tensor product will end up having 2 sets of independent Bernstein polynomials in each of the independent variables, U and V here. And the addressing scheme on these B, I, J control points will again be running over I and J independently, say for 4 control points in each direction. Yeah?
This shows, answer the question if I solve 2 summations.
This would be another way to convince yourself of that. Yeah, so here you can see the symmetry of being able to swap those. Yeah. There are other ways to think of this subdividing scheme too. I'll just mention that instead of doing it linearly, separately, you can actually do it purely in 2D. So you could take the 4 control points and then sort of interpolate them down into, instead of along a line and cutting corners, you can sort of interpolate it from 4 down to, in 2D, 2 by 2, down to a smaller 2 by 2, no, 2 by 2. But I'll just mention that, but I decided not to cover it in this class a couple of years back. But I'll mention it at least. Okay? All right. Continuity, let me just do this quickly. This is going to be very similar to the curve case. A little bit richer, of course, because we have a surface here. So if you have 2 Bezier curves and you want them to meet together, continuously without a gap of any kind, then you're going to need the 4 control points between the 2 curves as shown in red here. You need those to match between the 2 4x4 control nets. Okay, pretty intuitive. Then you end up with a C0 continuous surface. It could end up being, not like smooth, running smoothly across it. You could have actually an edge along there, okay, but it would be continuous, watertight. If you want it to be C1 continuous, so the first derivative across that portion of the surface is continuous, then you need this construction for each of these sets of points that I showed before. So this segment and that segment need to be the same length, and they need to be linear across those 3 points for each of these structures here. And then if you want it to be C2 continuous across that interface, you need the A-frame that we talked about before for each of those segments there. Okay. All right. And that is splines and smooth surfaces. And so any questions about this before I move and we start talking about polygon meshes and geometry processing on meshes? Yes? Yeah, great question. So this seems to work if we have quads and for smoothing out sort of, quad-like polygon meshes, you could imagine. But what if we start with a triangle mesh, which is much more common? So it turns out that would be great. And it turns out to be mathematically very difficult to do. But it has been worked out. It took a long time to work out. And the class of objects is called subdivision surfaces. And that's going to be one of the geometry processing things that we talk about next when we talk about meshes. Okay, but it's going to use similar sort of, it's not going to have the algebraic form that we had here anywhere near as easily. You could try to derive it, people have, but it's hard to do. But the geometric version, not the algebraic, but the geometric version of corner cutting, it'll look like qualitatively, you're like, yeah, I can totally see how that's a continuation of this. Okay, another question over here? Question? Yeah. Yeah, good question. So what happens if you try to constrain? Can you extend that A-frame construction higher and higher? And to be honest, I've never thought of that A-frame construction for higher order Bezier curves. There will be some analogy to it for sure. Come in, we can chat about it some more. But for the cubic Bezier curve case, which is the main focus I had here, where you have a 4x4 control net, right? You're going to bottom out because it's going to be given by a. It's going to be given by a. What's the word I'm trying to look at? Cubic. Oh my God, my brain's not working. Sorry. It's going to be given by a cubic polynomial. Okay, so if you just think of a cubic polynomial, at cubed plus bt squared plus ct plus d, then once you take 3 or 4 derivatives, it's like 0, right? So you're for sure guaranteed it's going to have all the higher orders of continuity by that fact. So there's not a lot of interest. You will get them, but there's not a lot of interesting things that happen. But once you have the A-frame construction and you have C2 continuity, that's the condition under which you know that that final joined object actually is just one Bezier curve or one Bezier surface itself, okay? And that's why, as I mentioned before, like you can take one Bezier curve and chop it in 2. If you chopped it in 2, it would respect this A-frame construction. Another question? Okay, let's talk about meshes. Okay, so we'll start talking about mesh representations and geometry processing, which will take us into next week. Okay, let's start with simple triangle mesh, okay? Very similar to stuff we've looked at. Here's a small triangle mesh composed of 8 points, 8 vertexes, and 12 triangles, okay? 6 faces, divided in 2 triangles each, so 12 triangles, okay? And here is, in contrast, a very large triangle mesh. This was a laser scan of Michelangelo's David sculpture in Florence. And laser scanning, laser triangulation was used to measure, right, empirically analog what the many surface positions are, and then that was the surface positions were meshed together to give a very fine-grained surface representation. This has, 28 million vertexes, 56 million triangles. Actually, they're so fine that you can actually see like the chisel marks of the artist's original chisel marks in this surface. Okay, so we might really care about the resolution and quality of surface representations. And this is a very, very large triangle mesh. So from Google Earth, a mesh constructed from satellite and aerial photography using computer vision methods like finding correspondences, so you know from multiple positions that you're looking at the same point, and being able to use those stereo positions or different viewpoints in order to deduce geometrically where that point must sit in 3D space. Since you use satellite images, you have a lot of pixels to work with, so you could have a lot of features over a lot of objects, giving you super detailed triangle meshes over very large and complex geometry, like a city. Digital geometry processing can be thought of that's a sort of very extreme case, but let's say you want to sort of measure, your body. So you could use like a Kinect or something and get a point cloud. And then you want to be able to take that point cloud and then do some processing of it geometrically down to triangles. Maybe you want to simplify it so you can send it over a network for a network game where your representation is going to sit in some kind of shared virtual world. Or maybe you want to process it down if you scan something, like say a statue of like an object, and then you want to be able to process it into a format that you could send to a 3D scanner to print it out. In this case, it's like a 3D mesh of like a blue bunny. Okay? All right. So a very high level sort of geometry processing pipeline. This could go in many, many different directions, but one common form you might imagine is you scan some stuff. You want to process it from point cloud into some kind of mesh representation, clean it up, compress it, do some other kinds of manipulations on it, and then maybe print it. Or maybe transmit it over the internet for someone else to view in a graphics program, like in VR, for example. Okay, so it could go in different ways, but it gives you sort of an idea into the themes or the kind of uses that we're looking at here. So let me give you 3 geometry processing tasks that are a little bit more fine-grained and ones that we're going to be looking at in this section of the course in some detail. So one is an example of gaining higher resolution through interpolation. We can call this mesh upsampling by subdivision. So for example, on the left, you have a polygon mesh, a triangle mesh here, and then the triangles are being divided. Each triangle is being broken into, in this case, maybe 4 triangles, whatever. You could start with one triangle, break it into 4. You could do it recursively, so you get a higher resolution mesh on the right. A different way might be, let's say you have a very high resolution mesh, and you want it to be lower resolution because you want it to store it more compactly. So this would be a simplification task. Given a high resolution mesh, how do I end up with a lower number of triangles and still approximate the same surface accurately? If you rasterize these two, would they look the same, as an example? Another might be, hey, I got a mesh, but it seems to have like some irregularities to it. As you can see on the right, like some triangles are big, some triangles are small. Maybe for some reasons, and there's certain kinds of other processing you might want to do on top of certain meshes, that it's helpful for them to be well-conditioned. One example of being well-conditioned could be that the triangles are all similar size, that they have they have the same valence as much as possible. Valence just means every vertex, how many triangles does it surround it. Maybe you want that number to be the same. So you can just look at the one on the right and be like, it looks more regular. Okay, so maybe some kind of regularization might happen here. By the way, the upsampling and downsampling we've seen in many forms already. It's related to some of the supersampling things we looked at. It's related to like images and upsampling and downsampling, for example, in bitmaps. Quite similar in spirit to that. This regularization one is not one that tends to come up when we look at image formats because those are on grids. So for surfaces, there's an additional sort of topological and connectivity issue that comes up that makes it significantly more complex than dealing with regular grid data structures like images. Question? Great question. Yeah, what happened to the ears here? So in this particular geometry processing, in order to make it regularized, some error has been introduced. Okay, like actually the part of the ears have been filtered off on the right-hand side. And so maybe you could do a version of this that did a better job at that. It regularized without causing that problem. But in general, right, this is going to be really a hard thing to do if you have a lot of detail at the eye, because you have a lot of detail, like eyelids and things like that, but the surface snout of a cow is like very smooth, then you could compress it by having few triangles on the snout, but you probably need a lot of triangles on the eyelids to capture those creases. So if you want to regularize it, then you kind of have to decide, are you going to really end up with a lot of triangles that are small, or are you going to allow having a sort of an intermediate size and lose definition in one place or another? Okay, so there's going to be trade-offs that have to be made when you choose the final forms of these outputs. Okay, so in this lecture, we're going to talk about how to represent meshes, data structures for doing that, and we're going to study how to process meshes in a few forms, give you a flavor for it, which we're going to call geometry processing. So I'll start with mesh representations. So in some sense, we've already been dealing with this, right? Because rasterization, you got to deal with triangles. So you're getting handed 3 triangles at 3 points, and they're defining triangles. No problem. You're off to the races. So one way to represent triangle meshes, obviously, is just a list of triangles. So in memory, if we have like an array of triangles here, first triangle, second triangle, so on and so forth, many triangles, and then 3 vertexes. So this is the coordinates, XYZ coordinates for the first vertex, second vertex, third vertex, okay? Just have a big, long list of it. You can think of this as a triangle soup. Triangle soup is another way, right, of thinking of it. Okay, so that's one way. A different way is to break this up a little bit and give the position of a whole bunch of vertexes. So vertex, first vertex, second vertex, so on. So just x0, y0, z0. And then the triangle data structure will be more like an indexing scheme, right? So this would be an index triangle data structure. So we'll just say, okay, the first triangle is given by vertex at index 0 and 2 and 1. So, where is it? Oh, that's XYZ, XYZ, and XYZ. Okay, clear. So start simple here, okay? Nothing crazy is going on. A simple comparison. So the triangle list case is super simple, right? Super simple, easy to understand. But there's a lot of redundant information. So if you have triangles that are on a watertight mesh, and you're just going to describe the same XYZ coordinates, say 3 float values, right? You're going to describe them again and again, repetitively, okay? For every triangle that shared that vertex. So it's going to be redundant and probably less compact for connected surfaces. In the point and triangle index sort of case, there's shared vertex, which will reduce memory usage. And another nice property is that it will ensure the integrity of the mesh in a certain sense, so that if you move one vertex as a thought experiment on the mesh, then it will, and it's a watertight mesh, and you move one vertex, it will stay a watertight mesh, right? Okay, because obviously all the triangles that point to it are connected to it through a pointer. Okay, let's warm up some more. So one thing that happens in these representations right away that you'll notice is you could have 2 meshes that describe the same shape, but the meshes are different, okay? And so we'll describe that as the topology of the mesh versus the geometry of the mesh. So the geometry is the shape of the surface. So these 2 meshes here have the same geometry, but different mesh topology. Oh, yeah, they do. Okay, right. Different mesh topology. Where is that? Okay, so many of these triangles are the same, but if you look at this face, there's 2 triangles this way, and then this. If you look at this one, there's 2 triangles the other way. Okay? But if those vertexes are in the same place, then we would describe the same cuboid shape. And this one is an example where the mesh topology is the same. The connectivity between the vertexes that defines these triangles has the same structure. In fact, if you think about that in the index structure, then the triangle data structure might have exactly the same indexes in it, right? It'll point to the same vertex locations, except that these 2 things have different geometry because one of the vertexes is in a different place. Okay, so notice this differentiation between topology and geometry. Okay, so this leads to the notion of topological mesh information. So, and it can guide us to sort of think about, as you're trying to move around a mesh, what kind of properties do you want in the data structure to be able to navigate over the surface, so to speak? For example, maybe you want constant time access to neighbors. That could be a useful property. It starts to sound a lot like, linked lists or other data structures or tree data structures or graph data structures, right? So similar sorts of calculus and considerations will show up here. So maybe you want constant time access to neighbors because you want to do a surface normal calculation or approximation for a vertex. We talked about that a couple of lectures ago. Okay, so I want to find all the triangles. I'm at a vertex, conceptually speaking, in an algorithm, and I want to find all the triangles that connect to me fast so that I can estimate their surface normals and then average them together to write down a normal vertex estimate for my vertex position, my surface position. Okay, or subdivision. Okay, subdivision is like I want to go through all the triangles and then I want to break them into more triangles. So I guess when I get to that position, I want to be able to insert constant time access. Do I have something? Okay, editing geometry. You might want to be able to add or remove vertexes or faces being the triangles in this case, or edges, things like that somewhat efficiently. Okay, so to drive certain algorithms, different data structures will give us different access times and different sort of rates. And the solution space that we'll be looking at is in the space of topological data structures. We're going to call this as topological data structures, okay? All right. Now, one of the properties that's really important for these topological data structures is going to be a manifold condition. So let me just tell you what it is, okay? So this is like a property of a surface that is going to prevent it from getting mathematically weird. That's the way I'll sort of put it. Manifold property is going to mean that the surface is sort of well-formed in many ways that we want. So a definition, a 2D manifold is a surface that when we cut it with a small sphere, okay, will yield something that looks like a disk. So there's some kind of smoothness to this thing, and there's something about it not intersecting itself in weird ways, okay? So let's look at a few examples. So on the left-hand side, this is a little bit strange, okay, when you think about a polygon mesh that has sharp edges, what this continuity thing means, the smoothness thing, so let's kind of walk through it. So these are manifold in this sense, in this definition, even though the surface is not smooth because it's segmented, these still are manifold. So if you look on the left-hand side, you have two triangles, and we cut it along the edge. We get something that looks like a folded disk, but we're going to say that is topologically a disk. Similar to the top of the pyramid there, if we cut it out, we get this sort of like, sort of folded little square, folded circle, a folded disk, but we'll still say that's topologically a disk. So what do we mean by non-manifold? So these things are examples of what we mean by not manifold, okay? And right away, I think you'll see why we might care about this. So here's an example of some bag of triangles, which we could represent in one of those index triangle data structures. No problem representing this. But it has this property that if you cut a point along this edge here, you do not get a disk, right? You see that? You have like some piece of paper object that has two parts that are sticking out of it. Okay. Similarly, for this, a point, a vertex that connects two objects and that are touching at one point, this is not a manifold either by our definition, because if we cut it right at that vertex position, we'll end up with this sort of weird thing. Now, why do we care about this? Because if we can have conditions like the ones on the right, you could imagine that when you're trying to write an algorithm, you might have to have a lot of really weird cases that you have to deal with. If I'm on an edge, for example, and I'm like, I want to know the two triangles on my left and right side, because I imagine I'm on some kind of watertight, normal-looking, quote-unquote, normal-looking mesh, then if I go try to look it up, I expect to find two triangles, but in those other cases, you might not have two triangles. Okay, so manifold is going to allow us to make a bunch of assumptions that will be strong, but they're strong assumptions, but they will yield a lot of invariance that we're going to count on in the algorithms. Yeah, question?
A little bit confused about the definition here. Like, how do you cut the 2D object?
Yeah. So the question is, like, well, what do we mean by cutting with a spear? So think of this polygon mesh as like, literally like a three-dimensional object. It is a surface. It's a segmented surface, but it's a surface. Okay. And then we take, by cutting with a sphere, I mean literally take a sphere, an infinitesimal sphere, tiny little sphere, and you go to a point on the surface, You're shown 4 points on the surfaces in these cases. And then we cut out what that object, what that surface looks like. And the question is, what do we get? So if we cut it with an infinitesimally small sphere and we get something that is topologically like a disk, we're in good shape. If we don't, like the ones on the right, then those are we're going to be calling not manifold. You might be interested in those too for other types of geometry processing that deal with really weird sort of cases, theoretically or otherwise. For this class, starting with the simplest case. Manifold is simplest case, okay? But this can get weird fast. Is one of the things you can take away from this, so we want to start in a cleanly position. Yeah. We're not going to go into any dirty positions. We're just going to stay with this sort of simple case and find it's complicated enough. Yeah. Yeah, are there, shapes that are inherently not manifold, or is it sort of these sort of weird corner cases? That's a good question. The way that I'm sort of approaching this is really more from like what we can assume about the underlying data structure. So it's mostly going to be weird conditions like this that we're avoiding. But the definition of manifoldness or the classification of it would sort of get into like, branches of mathematics and then computational or discrete mathematics, particularly dealing with digital geometry processing that get pretty deep. And I'm not a specialist in those areas. Good question, though. Yeah. Great question. What if we have an edge? So a very simple case. Let's just say we have a disk, okay? So this manifold thing, what if anywhere inside the disk, no problem, okay? But let's say I go to the boundary. Let me pick a better example. Let's say I have a skirt, okay? So I'm wearing a digital skirt here. So I go to the bottom hem of the skirt. I'm like, so is this a manifold surface or not? Because if I go right onto the edge and I cut it, I got a half disk. Is that the same as a disk? It wouldn't be, okay? So a manifold actually requires some kind of smoothness and continuity to the whole thing. There's no edge to it. We're going to allow manifold with a boundary. Okay, so there'll be like a boundary edge will be okay for our perspective because you want to represent a lot of things that have edges typically. So that's will be an exception, but that's okay. That's like one sort of class of things that we can make our algorithms deal with because it's super useful. But we're not going to deal with like just arbitrary collections of connectivity in our topological data structures. Is the main point. Question, yeah.
We don't care like if like say two like curves, two like triangles are like visually, but like as long as they're not connected.
Good question. So like what happens if you have a surface and it's sort of overlapping itself, but it's not in the topological data structure? Good question. And they will deal with different, you're right, that by the definition here, this mathematical definition, at least the sentence, that wouldn't be manifold either. In terms of how we might represent it as a mesh, we may not have any inconsistencies of the kind that I described we're trying to avoid in that topological data structure. The focus here, the reason I bring this up is when we get into these topological data structures, I want to be able to make certain assumptions. Okay, yeah. Question, yeah.
I just wanted to ask about like how small the spheres have to be.
Yeah. Yeah, good question. Good question. Think of it as an infinitesimally small sphere. So we're just looking for sort of local continuity. Okay. Let's continue on. So good questions. Oh, good questions. This was the border question that was answered. Okay. So these would be not the same as a disk, but we're going to allow manifold with a border. Okay, and you could have non-manifold with a border as well, which, as you can see, is a little bit different. So the one on the right, you have a certain point there where when you look at it, the border edge is touching another border edge. So we're not going to deal with that, for example. Okay? All right. If you have this manifold property holding, then a bunch of wait, what happened here? Okay, then we can rely on a bunch of useful properties. So we will be able to rely on one edge connecting exactly two faces, except at the boundary. An edge will connect exactly two vertexes. A face will consist of a ring of edges. And a ring of vertexes. And you can see that these will not hold in the manifold case. And a vertex will consist of a ring of edges around it and a ring of faces around it. Okay? Also, it's a little random, but many other things will hold. One of them, for example, is that there's a Euler formula for a polyhedron. So if it's if it's topologically equivalent to a sphere, in addition to being manifold, then the number of faces minus the number of edges plus the number of vertexes will be equal to 2. Those are very strange and very specific and random, okay? There's sort of a general case if you have like handles and other things. But anyway, so my point is that once you have this certain property, there's a number of things that you can count on in order to calculate or rely on in your algorithm or deducing other things. We'll come back to this Euler formula a little bit later. You can check for a cube, for example. So a cube is like 6 faces, right, minus 12 edges in a cube, plus 8 vertexes, and that equals to 2. And so anything that is, even if it's a million triangle mesh, but it's topological equivalent to a square or a sphere, then it's going to have the same property. Yeah. Oh, thanks. You might need to take participation. So I don't forget. I'm going to get there, but why don't we do it first? Okay, let's do attendance. Thank you for that. Okay, so for these topological data structures, as I said, so one important property we're going to assume is manifold with a border, with an optional border. The second other condition, the last one, is going to be orientation consistency. Okay, so what does that mean? It means that it's sort of like a winding, one way to think about it is a winding order. So if I take any particular triangle and I say here's vertex 0, 1, 2, or 1, 2, 3, okay, then that'll define a winding order, say by sort of a right-hand rule in which way your thumb's pointing. And you can see on the left, both of those triangles, if wound in that particular direction, would have a similar anti-clockwise orientation. On this thing on the right-hand side, that's not true. This one, the orientation is the other way. Okay, so this one's counterclockwise and this one's clockwise. And so one thing we're going to assume is that we can, for our surfaces, that they're orientable. So you can make them all consistent. You can make all the triangles and their winding order, which is going to be important, point in the same direction on the surface. There are inherently non-orientable surfaces, for example, like a Mobius strip, right? And we're not gonna deal with that. Okay. Manifold, orientable. So, so the triangle neighbor data structure is the first topological data structure I want to talk about. Okay, so what does it look like? Here's the data structure definition. So here's the structure for this triangle node. It has 3 vertexes, pointers to 3 vertexes. And it has a pointer to 3 triangles. There's a vertex structure or vertex node. It contains a point P, so in this case the XYZ positions of this vertex. And it has a pointer to 1 triangle. And in this case, that vertex will just point to any one of the triangles that surrounds it. Okay? It's a bit curious. If you look at this, you're like, well, why doesn't it point to all the triangles? This is the definition, okay, of it. So let's see what happens. So let's say you have this triangle here, and we want to do a mesh traversal where I want to find the next triangle counterclockwise around vertex V from triangle T. So I give you a vertex, and I give you a triangle, and I want to know the next triangle around when I wrap around that vertex from triangle T. Okay, so how do we do that? So we'll call that next triangle counterclockwise from vertex. I give you V, I give you T. So what do we do here? Okay, so let's take a look at this. So if the vertex I'm given is equal to the triangle's first vertex, then I can return TV0. Right, then I return the first triangle on the list. If V is equal to the second vertex in the triangle, then I'll return T1 over here. If V equals the triangle's V2, that'll be this guy over here, then I'm going to return T2. Okay? So again, it's counterclockwise around vertex V. So if T is equal to this guy over here, then counterclockwise would be, counterclockwise would be here, T0. If T happens to equal V1 of this blue triangle, then counterclockwise around it would be, T1. And if V equals V2 of this blue triangle, then counterclockwise from V equals to T2. Okay? So you can say, I want to do this perfectly reasonable thing, like I want to traverse my mesh and define some kind of addressing scheme and say, how do I get around it? And then this is an example of an algorithm that, a geometric algorithm, traversal algorithm that acts on this topological data structure. Okay? So this is one simple example on a simple triangle, what do I call this thing? Triangle neighbor data structure. Okay? This data structure points you to the neighbors of a specific triangle and its vertexes. There are many, many topological data structures out there. The one that we're going to focus on for this, most of this class, is a little bit more complicated than the triangle neighbor data structure, but it's very common and is related to a class of topological data structures, a family of data structures that has very similar characteristics and sort of takes similar tactics, data structure tactics and algorithm tactics to this one. This is called a half-edge data structure. Okay, so let me walk you through it. And again, the purpose of this will be to allow us to have ways to navigate and roam around a mesh, but have an efficient way to represent the whole thing. You can sort of think of this as like a linked list kind of representation for the mesh structure. Okay, so the core part of this data structure, there'll be a few related classes in a second, but the core one is called a half-edge, and the key idea is that for every conceptual edge in this mesh, we're going to have two half-edges that act as a glue between the two mesh elements. So those two half-edges would be called, here's one half-edge, here is its twin. A half-edge also has a next half-edge by roaming around the face that it sits on, that it lives in. So if I want to be on a half-edge and go to the next triangle, I can look up its twin. And if I want to go around the face that I'm on, I can use the next pointer. And that's represented here. So a half-edge has a pointer to its twin, has a pointer to the next half-edge, and has a pointer to the vertex. That is the beginning, like the starting point of that half-edge. It's an oriented vector, right? So this is the vertex at the beginning of that, on the starting part of that half-edge. The half-edge also has a pointer to the edge that it sits on and has a pointer to the face that it's a part of. So a bunch of pointers. Question, yeah? Good question. So the question is, why is there only one face defined here? So the reason is that this is the half-edge that we're talking about. So this data structure here is referring to this half-edge here on the conceptually the left half of this geometric edge, okay? So all the things, the pointers, this describes all the pointers that are attached to this half-edge structure. The next, the face, the edge, and then also to the twin half-edge, which is on the conceptually the other side of that geometric edge and is composed of the other triangle. So if I want to get this face, no problem. What I do is I go from this half-edge, I follow its pointer to its twin, And then that half edge will have a pointer to the face. Does that make sense? Yeah, good question. So this is a way of how you traverse through. Yeah, question. It will go. The next vector will be guaranteed to traverse the triangle that it's on. So if you keep going next, you logically will have to come back to the current half edge. So you traverse that face that you're on by next until you come back to the same vector that you start on. Okay, so let me just finish out this definition. You have the half edge. There's also the vertex that's pointed to, structure, the edge, and the face. These are pretty simple, okay? So the vertex itself is where we store the actual positions of everything. So the vertex has a point PT, which would be the XYZ positions, and it has a pointer to the half edge. Each edge has a pointer to a half edge, not defined which one, actually, okay? Interesting. The face has a pointer to a half edge, not 3 edges, half edges, or so on. In fact, you could represent not just triangle meshes this way, you could represent general polygon meshes this way, so you just point to one half edge. Now, why not all of them? Because you don't need to, because when you find one half edge, you can just use next to get all the way, traverse the boundary of the face that you're sitting on. Make sense? Okay. So, as I mentioned, you can use the twin pointer and the next pointer to move around the mesh here, and you can process vertexes, edges, and or faces as you traverse the half edge structure. So let's do an example. Let's process all of the vertexes of this one face here. I already described conceptually how it works. I give you an input half edge. I give you a face. Let's initialize a half edge H by taking the half edge that's pointed to by that face. And we'll just do repetitively. We'll process the current half edge's vertex. That's going to be the vertex in this diagram down here that is this one down here, okay, connected to that half edge. Then we'll just advance the current half edge to the next one. So start here, moved over there. Great. Just keep doing that, and that will serially process all the vertexes around this face. And we stop when we get back to the face's original half edge. Okay? Let's do a different example. Let's process all the edges around a vertex. So let's say I give you this vertex here, and I want to process each of the edges, the 6 edges that surround this vertex. So I give you V. Again, let's initialize a half edge H. And then what we'll do is we'll process the edge that this half edge points to. And then we want to get to the next edge. So if this is the half edge here, let's say in this case, we'll go clockwise, okay? So we'll go from this edge, follow it to its twin. We'll take that twin's next pointer, and that gives me this half edge here. And that's exactly what we do here. So we advance H to the next, to the twin, and then to its next. So you just wind around and process all those half edges until what? Until the half edge, this H is, back to the half edge corresponding to the input. Okay? Let me tee up what we're going to talk about next time. We'll start talking about local mesh operations, okay? So you have basic operations for data structures like a linked list. For example, you want to insert stuff, you want to delete stuff. The basic operations for a half-edge mesh look like this, okay? They're called flip, split, and collapse edge. So let's say that I have a particular half edge here. It's going to be connecting 2 faces. I conceptually want to keep that same geometry, but I want to flip that edge from, in this case, vertical through these 2 triangles to horizontal. It's called a flip. You could have a split. I could take this half edge and the 2 faces that it connects, and I want to split those 2 faces so that I form 4 triangles instead of 2. Or I could take a half edge and I logically want to delete it. If I delete it, we have to consider it's 1 ring. If I get rid of it, these 2 vertexes are going to become 1, and I have to reorder a bunch of edges and faces here. Okay? When you do these, you have to allocate and delete elements. You might have to reassign pointers, similar to a linked list, but with a lot more structure. Okay, so and care is needed here to preserve this manifold property in certain conditions. When you have these basic operations, you can amalgamate them into global mesh operations that I alluded to beginning. Subdivision, simplification, and sort of reconditioning, like remeshing. We'll talk about those next time. Thanks, folks.